Hi, this is Big Tuition, and this is a quick review on the chapter of summation and series. So to start with, we talk about summation. In summation, we begin by starting with sequences, which is a group or set of numbers that follows a rule or pattern. So each number in this sequence is called a term. So each term can be described with an algebraic expression that defines the pattern of the sequence, either in terms of n, which represent the number of the term, or in terms of the previous term, t n minus 1. Okay? So if I tell you that if it's given in terms of n, which tells us the pattern of the algebraic expression, I can tell you what is the 10th term, and immediately you can give me what exactly it is in terms of n, right? Whereas in the case of a recurrence relation, where you have the pattern defined by a relation with the previous term, it might be a bit harder. But either way, these are both sequences. And when you sum them up, you get a series summation. Okay, it's called a series summation. Usually this is done in a sigma notation, where you have basically a big sigma, where they tell you where to begin the summing x and where to end the summing x. So if we have a function that is of x that is being summed, basically we just need to substitute the x into it. We substitute a into x, a plus 1 into x, so on and so forth, and we add them all up. So we see that this summation equals to fa plus fa plus 1 plus fa plus 2, so on and so forth, until we sum to b. Note that in a series summation, the step is always plus 1 in what is being changed. Okay? In this case, x is what is known as the dummy variable. So a dummy variable it's just a variable. It's just an unknown that is being changed. So it's like you are having two unknowns usually, because usually a series summation would have two unknowns. One is being changed as you sum up the entire series, and the other is the actual unknown that you later want to express as a complete function. Usually it can be something like, we'll see that. Usually this is easier to do with examples, but basically the sigma notation is when you sum up, and depending on what you are summing over, here we are summing over x, we have to change each and every term, change the x of each and every term, and sum them all up. The number of term will be given by the ending term, which is the b in this case, minus the initial starting one, then plus 1. So why plus 1? This is just a matter of how we count. Because let's say we count from 1 to 10. Okay, we count from 1 to 10. How many numbers are there? There are 10 numbers, right? But 10 minus 1 is 9. You have to add back the original number. That's why you plus 1. Then equals to 10. So it's just b minus a plus 1. Okay. For sigma notations, there are some properties. They are distributive. What this means is that here when you have two summations that are added up within the summation, you can actually break them up and sum them up first. This for example, if let's say we have summing of xi plus yi, and we have I equals to 1 to n. What this means is we can write it as x1 plus y1 plus x2 plus y2 plus all the way. Note that now we are summing over I, not x. So our x will be a pattern that is based on I. Okay? Previously we are summing over x. So what we sum over can be anything, can be any letter. We just need to make sure we know what is being changed. So we have x1 plus y1 plus x2 plus y2 plus until xn plus yn. We can regroup them to give us x1 plus x2 plus until xn, then plus the same thing for y1 plus y2 yn. Then we notice that this is basically one summation on its own. This is another summation on its own. And this is why a summation, a sigma notation, can be distributive. Second property is constants can be factorized. When we are summing over a term that has a constant multiple applied to it like this, like k, we can actually basically just factorize out the k from all the sum, and the k will be outside the summation instead. This is basically like, let's say there's a k here, so there will be k, so on and so forth. No, there's no k in front of the y. So here, then there will be a k in front of all the x, and there's nothing wrong with just factorizing k from all of them and writing it outside the summation. And this is why constants can be factorized. And then limits can be split up. This is basically like if you're adding from the first term to the fifth term, you can then add from, let's say you want to find the sum of first to the 10th term. You can split it up to find what is first to the fifth term, then 6th to the 10th term. Okay? So this is just breaking up the summation into two parts. And finally, the limits can be changed because what we are summing over, the dummy variable I, can also be changed inside the pattern. Okay? So basically, instead, we can add n to all of the dummy variable that we are summing over, and then in the actual pattern, we just subtract them. So in the end, we are actually summing over the same pattern. It doesn't change the pattern, it just changes what sum we are doing. This can be useful usually in questions where they ask you to simplify the summations. In fact, all these summation properties will be useful when they give you like adding up two different sigmas notation and you want to bring them into one. Then you can use all this to help you manipulate them such that they become one single sigma. Okay? So we move on to examples of these summations. First one being arithmetic progression. So arithmetic progression means that each term is bigger than the previous by the same amount. Okay? In a more mathematical way is that it has a common difference from the previous. So whichever term you have is bigger than the previous term by d, which is a difference. This common difference can be positive, the sequence will be increasing, negative, where the sequence will be decreasing, or zero, so the sequence will be staying constant. It is still considered arithmetic progression if it's constant. So if you have like 3, 3, 3, 3, 3, that is also an arithmetic progression with a common difference of 0. To show that a sequence is arithmetic, we just need to show that a general term, Tn, subtracting Tn minus 1 give us the same value of a common difference. Note that this must be done for a general term, okay? Because if it's a very specific term, it may be a pattern that is only valid for those few terms, which may not always be true, may not be true moving forward, right? So we should do it algebraically to show that it will be a common difference. And when and the general term Tn is denoted as this. Okay, using a general term, we can see why the common difference will be d lah. So for example, Tn equals to a plus n minus 1d. Tn minus 1 is a plus n minus 1 minus 1d. And Tn minus 1 give you a minus a is nothing, n minus 1 d minus n minus 1 minus 1 d. In this case, we just write it as 2 lah, minus 2d. This will give us, this will just give us d. And we can see that difference, this is what is meant by a more algebraic way of showing it lah. So we cannot take two numbers and we just show that the difference is constant. After getting the general term, their general nth term, we need to sum them up. So summing them up will give us these terms, this sum, which also equals to this. How we think about this is that n over 2 to 2a, okay, let's say we have a arithmetic sequence where we have a constant difference. So we have t1 plus t2 plus t3, so on and so forth, until tn minus 1 plus tn n. We notice that from here to here is plus d, from here to here is minus d. So if we add t1, if we pair t1 with tn, this will be equals to t2 plus tn minus 1, and so on and so forth. Because each time t2 will be d larger than t1, but tn minus 1 will be d smaller. So that's why they are the same. So when we pair them up, we can write it as there's a total of n terms, right? So there are how many pairs? There will be n pairs. N over 2 pairs plus t1 multiplied by t1 plus tn. Okay, so if it's t1 plus tn, this is also equals to n over 2 t1 plus t1 plus n minus 1 d. So where did I get this t1 plus n minus 1 d from? This is given by this over here. A is the first term, so A is t1. And we note that this expression here is basically this sum. When we write the sum up like this, we see that we get n over 2 t1 plus n minus 1 d, which gives us the other form of the summation. Okay? So that is how we arrive at the sum equation for arithmetic sequence. The nth term can be found by taking the sum to n, subtracting the sum to n minus 1. And the arithmetic mean is just given by the sum of all the terms divided by the number of terms. This is actually how we normally find average. One thing to note is that observe that Tn in an arithmetic sequence is an arithmetic mean of the previous and next term. This is just a nice thing to note. Not often that this will be tested, but nice thing to just know. So now, arithmetic sequence is adding up, right? Adding up with a different difference. We have geometric progression in which each term is a multiple of the previous term. In this case, that multiple is called the common ratio and is defined to be this. So R equals to the nth term divided by the n minus 1 term. The common ratio can have absolute value of R more than 1, the sequence will be increasing. R less than 1, the sequence will be decreasing. Or R equals to 1, where the sequence stays constant. And in the case where R is less than 0, the alternate term flips sign. Okay, note that here I wrote that there's absolute value, right? These are absolute value. Yeah, because we are just talking about the absolute value of the sequence increasing or decreasing. If it's less than 0, all that is different is that the alternate term flips sign. To show that the sequence is geometric, we need to show that the ratio between a general term, Tn, divided by Tn minus 1 equals to R. Again, like before, this should be done for a general term, algebraically, and not just specific numbers. Given that the first term is A, we can write that the nth term is AR n minus 1. Here there's quite a bit of, usually in this chapter there's quite a bit of confusion with all the minus ones, but just remember that the first term is just equals to A. There's no R. That's why every R will have a power of n minus 1. So the sum of the first n term of the sequence is given by these two expressions. Okay, it's given by these two expressions. The only difference between the two of them is that you multiply by minus 1 on top and below, in the numerator and denominator of the fraction. Okay, you should try and derive this. You can write it as you can write the sum out explicitly as an equation, then multiply both sides by the common ratio and subtract the original sum from the equation. This is a very good hint. Just try it. It helps with practicing your algebraic manipulation. And sum to infinity exists only for absolute value of r less than 1, because then the sequence will become smaller and smaller and smaller. If r is not less than 1, if r is 1, then it's a constant term. So when you sum to infinity, you just keep getting larger and larger. If r is more than 1, then even worse, because then each of your terms become larger than the previous term, and eventually you add a larger and larger number to your sum, and it won't converge. Okay, the property of having a sum to infinity is known as convergence, which is given here. It means that the sum eventually approaches 0. Sorry, the sum eventually approach a constant. Okay, so sum to infinity, denoted as S infinity, can be obtained by taking limits of the original sum. Actually, it's quite straightforward, because when r is less than 1, when modulus r is less than 1, r to the power of n approaches 0 when n approaches infinity. You can try to press in your calculator. Let's say your r is 0.5. Let's say r is 0.5. You can just try r to the power of like 10 would be something like 1 over 1024 or something, which becomes very small. If it's 100, then it's even smaller. So eventually the ratio just becomes very, very tiny. Then your terms become very tiny and your sum approaches a constant. One thing that is not so obvious is that the geometric mean of numbers is equals to them multiplying and then taking the nth root of it. This is not like directly related to this geometric progression, but could be useful, and also helps in the final point of note that Tn in a geometric sequence is actually the geometric mean of the previous and the next term. Okay, and we have Tn minus 1 times Tn plus 1, 1 over 2. This is a geometric mean of two numbers, right? And we can see that Tn minus 1 is equals to Tn over r, here, and multiplied by Tn times r, which is here. The r and r cancels, and you just get Tn squared in the middle, inside the bracket. 1 over 2, power 1 over 2 is basically square root. So this gives us Tn. Okay. With that, we wrap up the main concepts in summation. And I hope this helped with your revision, and happy studying.